Problem 43. Let x1 through x25 be a random sample of 25 drawn from a normal distribution with unknown mean, mu, and variance equal to 100. It is desired to test the null hypothesis mu is equal to 4 against the alternative that mu is equal to 6. What is the power at mu equals 6 of the test with rejection rule? Reject mu equal to 4 if the sum of the x's are greater than 125. So problem 33 is we're given that the xi's are normal mu with a known variance. So the distribution of the sum, the sum of normals is normal with n mu and n times the variance. So let's calculate the power, which is the probability that this summation is greater than 125, assuming the alternative is true. So we subtract the mean and divide by the standard deviation of both sides. We get this, and that's the probability. Problem 44. Let x1 through xn be a random sample from a distribution with density function given. Let y1 through yn be the order statistics of the sample and assume that n is odd and mu is known. What is the maximum likelihood estimator of sigma? So, exam 1 of 8, problem 44. Here we're given that the x's are from a known density, and we also they also let us know that about the order statistics, y1 through yn, where that's kind of a ruse. We don't need those. If we look at the joint distribution of the x's, so that's because they're independent, it's the product of each density of each xi, so that is this. So now we set the likelihood equal to that, and the difference is in the joint density, we are assuming that the x's are random and the parameters are fixed, but in a likelihood, we assume the x's are fixed and the parameters are random, and then we find the parameter that maximizes that. So we take, so what we do is we trick this. This is a pretty complicated function to maximize, but we know that if we take the log of both sides, since log is a increasing function, that maximizing this is the same as maximizing the log of it. And the log simplifies this equation. So we take the derivative with respect to sigma of the log of the likelihood. We get this, set it equal to 0, and we solve for sigma. So our estimate is n over the sum of the absolute value of the differences. Problem 45. A sample of size 6 was drawn from a normal population with unknown mean mu1 and unknown variance sigma 1 squared. If an estimate of sigma 1 squared is this, was calculated, and a sample of size 10 was drawn from a second normal population with unknown mean mu2 and unknown variance sigma 2 squared, an estimate of sigma 2 squared was calculated as the formula. It is desired to test the null hypothesis that the variances are equal against the alternative hypothesis that sigma 1 is less than sigma 2 squared. At the 95% level, using the statistic, which is the ratio of the sample variances. What is the boundary of the critical region for this test? Now, 45, it says, we want to test, are the variances equal or are they not equal? And it says to use this to test statistic. And then what's the boundary? Okay, so what's interesting is most F tables, we can't calculate this, okay? So this is a left-held test in F distribution. So remember, well, let's, you know, if we divide both sides by sigma squared, this alternative is this ratio. So it's a left-held test. But most F distributions, or the table that I have, only does the right distribution. So it says use this as our test statistic, which is distributed F59 with numerator degrees of freedom 5, denominator degrees of freedom 9. Remember, this is under the null, but which makes that a left-held test, because this one is smaller than that. So there's small values, but we could have, if we take the reciprocal, it's still an F. So, but it's 9 numerator, 5 degrees of freedom. And so we're going to have to use that for the tables that I have. Now, if you have tables that do a left tail and a F distribution, then it makes it simple. But here, we want to know that F is less than C. That's our critical region. But we don't have that. We can only do right. So if we flip this, this is our test statistic. If we flip and flip, the inequality changes, but then this is a F distribution with 5 and 9. So we're in this setting, and this is 0.05. But we want, my table is a cumulative, so I have to calculate this, that we're less than that, which is 95. Greater than that is 0.05. Well, it turns out that this value is 4.7725, and then solving for C, we get C is equal to 0.21. So this problem may have been made tricky based on the F tables that I have. 46. Suppose we wish a two-sided test of the hypothesis that the mean of a normal population is M based on a random sample of size 16. If the sample mean is 68 and the sum of xi minus x bar squared is 375, the hypothesis will be rejected at the 5% level of significance if and only if the absolute value of M minus 68 exceeds. So 46, we want to know the probability of this quantity right here, this quantity exceeding a certain value is at the 5% level, okay, this quantity. But note, since it's in the absolute values, we can switch those and it doesn't change. Okay. And I like it like this because this is a value minus the mean, and that's the way I think of doing setting up a t-test or a z-test. But in this case, it's a t-test because we don't know the variance. So the sample variance is this. Sample variance. So we want to know the C that makes this 0.05. Well, we've already subtracted the mean here, so let's divide by the standard deviation, which is this on both sides, and then this is a t-distribution with 15 degrees of freedom, and then this simplifies to that. And the standard deviation is the square root of 375 over 15. And then this quantity is 2.3. That, solve for C, we get C equal to 266. Problem 47. 100 pennies are being distributed independently and at random into 30 boxes labeled 1 through 30. What is the probability that there are exactly 3 pennies in box number 1? So problem 47 is, this is an interesting one. We want to know you know, the probability that we have exactly 3 pennies in box 1. So, and everything is random. So if we take 1 penny and throw it in, you know, randomly put it in one of the boxes, well, let's let xi be that the ith penny is in box I. So the probability that it's in box I is a binomial with probability 1 over 30. That's the probability that it's in box 1. Well, we have 100 pennies, so let's add those up. You know, it's either 0 or 1. So we're trying to find the probability that y is equal to 3. But because x is binomial and the sum of those are all binomial with the same probability proportion, y is binomial 100, 1 over 30. And this is the density. So the probability that y is exactly 3 is 100, choose 3, 1 to the 1 over 30th to the third, 29 over 30 to the 97th, and then that simplifies to this equation. Problem 48. N observations have been drawn independently and at random from a continuous distribution. What is the probability that the next observation will be less than all of the first n? So question 48, sample 1. This almost doesn't seem like there's enough information to answer this question, but there is. So let's think about the first n observations, not the n plus 1 that we're interested in. Since they're all equally likely, there are n factorial possibilities of these orderings, each one of those. And they're all equally likely. But now, if we let any one particular value, we say, you know, let xi be the smallest, then the way that we can order the rest of them are n minus 1 factorial, assuming that this is the smallest. So pick one of them to be the smallest, and there's n minus 1 factorial ways to order the xi's with, you know, with the data with xi the smallest. This is over the total number of ways to order the data, and so the probability is 1 over n that xi is the smallest of this. So now we want to find the probability that our next observation, n plus 1, is the smallest. Well, there's n factorial ways to arrange the data where n plus 1 is the smallest, and there's a total of n plus 1 factorial ways to order the data. So the probability that our next observation is the smallest is 1 over n plus 1. Problem 49. Let x be an observation drawn from an exponential distribution. It is desired to test a null hypothesis that the mean of the distribution is equal to 1. Which of the choices below is a 5% critical region to test hypothesis against the alternative that the mean is greater than 1? So problem 49. Now this is one of the ones that I think you could probably jump down to a spot lower in this solution, but I couldn't rationalize it, so I just solved it. So here's our null and alternative, that the mean is 1, or are we greater than 1? And we only take one observation. Now notice that when we find the mean of the distribution, it's actually 1 over k. So when we say the mean is 1, that's equivalent to saying k is 1. And if mu is greater than 1, that's equivalent to saying k is less than 1. Okay, so really we're doing this null hypothesis behind the scenes, but we're interested in this. So f of x is this distribution, and so the likelihood ratio is this, where you take the joint density, but there's only one value, so you take the density under the some value k, and then the denominator f of x given k, and you solve it to this. Now the reason I'm doing this, there's a theorem that says if this is a monotone likelihood ratio, then the test statistic becomes very easy. And so if, assuming k prime is greater than k, then this is an increasing function in negative x, okay? So if that's the case, then we reject h naught when negative x is less than c. But this also implies that we're going to reject when x is greater than c, okay? And so somehow I think you probably could rationalize that if we want the mean of 1, or is it really greater than 1, you could probably jump to this, the rejection region. We're going to reject if our x is too big, meaning the mean is much, much greater than 1. We're going to pick some c here. So to find that, we want to find the c. So the alpha is 0.05. The probability that we're greater than c under the null, well, you integrate that, and then you have to plug in our null value of k equal 1. Integrate, substitute in our limits of integration, we get e to the minus c. That is equal to 0.05. So you take the log of both sides, and then it equals the log of 20. And problem 50, after a certain time, the weight W of crystals formed is given approximately by W equal to e to the x, where x is distributed normally with parameters mu and sigma. What is the density function of W? So the last question on sample exam 1 of 8 is we want to find the distribution of W, which is e to the x, where x is normally distributed. So x is normally distributed here. And this is one of two solutions. So we let W be e to the x, we back solve for x, take the log of both sides, the derivative is 1 over W to the W. So the Jacobian of this transformation is 1 over W. So the distribution of W is equal to the x distribution with this x plugged in times the Jacobian of the transformation, absolute value of the Jacobian of the transformation. So it says plug in log of W wherever there's an x, which is here, and then take it times 1 over W. Well, we're finished. In some cases, it's easier to kind of set up a cumulative distribution function and then take its derivative. In this case, it's not, but we'll do it both ways as a learning tool. So this is the probability that W, big W, is less than little w. So that's a random variable, that's a value. Well, W is e to the x. You take log of both sides. We get probably that x is less than or equal to log of W. Well, x we know is normal. So we can integrate being less than log of W. And that's what we do here. Well, so that's capital F of W. Now we're going to use the fundamental theorem of calculus and the chain rule. So note that if we take the derivative of some integral, then that is the same as f of, you plug in this value for the f, and then take the derivative of it minus, you plug that value in f, and then take the derivative of it. That's the chain rule. And anyway, that's the formula. So if we look here, if we're taking the derivative of this, so we're going to plug in a log of w to here, and then take the derivative of that. So that's what we do. We plug in L of w, and then we take the derivative. Well, the derivative of log of w is 1 over w. Then if we plug in negative infinity here, then there's really no w to take, the derivative. So it's all constant. So you don't even need it. So anyway, that's two different ways to come up with the same answer. Hope you enjoyed the video.